Upon profiling, you may find out that your vertex shaders are exceptionally heavy, and this, in most cases, points to high poly counts. So how detailed your meshes can depend on the hardware you're using, and the lower end, then the less polygons generally you can use. An interesting thing to note is that mobile devices or GPUs that have the tiled GPU architecture are optimized for pixel efficiency more than geometry throughput compared to your standard immediate mode GPUs. They rely on fast but small on-chip memory, and if that on-chip memory is overloaded and we're forced to go into main memory, then geometry reads will be very slow. So having low poly counts on mobile devices is very important. One tip I can give is that if you have a detailed mesh that needs to be simplified, but you would still like to keep that detail in the scene, I would consider baking that detailed data into maps. So for example, a normal map to still keep that detailed lighting, or height maps for use in parallax shading. Next, we have level of detail, which is a system to switch from a high poly mesh to a low poly mesh as the camera gets further away and the relative size on the screen gets smaller, and it's no longer something we need at a very high level of fidelity. This in Qt Quick 3D is automatically handled in the mesh file if you specify so in the Balsam UI. But there is also a LOD manager where you can explicitly set the LOD, how many LODs you want to use, what type, and their distances, and so on. A consideration that I'd like to mention is to avoid triangles that are smaller than 2 by 2 pixels. GPUs generally process pixels at 2 times 2 quads, and every triangle then is rasterized as that quad regardless of if it's smaller or the same size as that 2 by 2 quad. So if you have a triangle that is only 1 pixel in size, then you will still rasterize it as a quad, effectively doing 4 times more work than needed. This is where level of detail sort of comes in. It allows you to get rid of those small triangles as you would get further away from the camera, and instead change those into bigger triangles that are much more GPU friendly. In instancing, if we have multiple objects, we can render that object in one draw call, as opposed to using multiple draw calls, one draw call for each mesh that we have. Important note about this is that it is a CPU optimization. So if you have the same object being drawn multiple times without instancing, you will often find that you are CPU bound, especially if you have a lot of these models. And instancing helps with this as it sort of packages those models into one, only executing one draw call. And it just provides the GPU with some extra data telling us where the mesh is and what its rotation, what its transform is. Getting into some more intricate optimizations for high poly meshes that have to be kept high poly, you can also consider improving cache locality. So the GPU caches the results or outputs of a vertex shader invocation in a vertex cache based on the vertex index. So this is sometimes called the post-transform cache. And what it does is it helps the GPU avoid executing the vertex shader when using them to create the primitives, so usually triangles. The cache can usually store 10 to 20 or sometimes even more vertices, but if the vertex is not in the cache when we're generating a primitive, it will have to execute the vertex shader. So rearranging the vertices and indices to be optimal can help us maximize that cache. And this is actually what improved cache locality does in the Balsam UI, which wraps the async library. It uses the tipsify algorithm, but there are other algorithms that might be more friendly for your GPU, depending on your GPU. I highly recommend looking through the Optimal Grid Rendering is Not Optimal blog post. In Qt, we can also use the Qt Quick 3D Custom Geometry class for some extra optimizations that we can do, such as, for example, vertex packing. So for making sure that the cache lines have a maximal usable data, similar to how kind of CPU caching of arrays of items might work, we can do the same here. So for example, the classical approach of packing your vertex data is to use an interleaved approach, where you essentially have an array of structures. In this case, your structure would be the vertex, and it consists of your position, your normal, your texture coordinate, and so on. And we just simply place that in memory as one block, leaving all the data, separate data together in memory. You can, of course, also use de-interleave, which is where you have a structure of arrays approach. You have all your positions placed first, then of each vertex. Then you have all of the normals of all the vertices next, and so on. And this can be a win for the cache line, as then if we're reading, say, just the positions for a specific operation, we can fit all of that nicely into the cache. An interesting thing worth looking at is this Vertex packing blog post by SolidPixel. He goes into an idea of splitting the streams, of combining the two, where for mobile hardware, it can be useful to have the position data de-interleaved, where it occupies one part of the memory, and then the rest of the properties as interleaved as an array of structures where properties sit next to each other. Then another thing we can do with Quick 3D custom geometry is we can compress properties. So these days, for example, normal compression is quite standard. And what we can do, for example, is compress normals into an int32, where we have 10 bits per axis with 2 unused or for some sign data. Now, this is technically a lossy compression as we lose some precision there, but this is often considered a acceptable loss in performance, considering there's not much difference in the visuals. But another thing we can also use, for example, is octahedral encoding, which also uses 32 bytes split into two 16-bit channels. And this is specific to normals, where we only care about the normalized vectors where the length is 1, which is a very small subset in all vectors of arbitrary length. So therefore, we can use spherical coordinates to store the memory more efficiently, effectively omitting length from the normal vector and getting much better compression. So here is a video of changing instancing and changing high poly to low poly. This is recorded from the Qt Quick 3D benchmarking application, and this can be used to benchmark the capabilities of your target hardware, as well as to see how different Quick 3D settings impact performance. A very useful tool. And this was running on my laptop's integrated GPU, so quite a low-end GPU. So we start off with a high poly mesh, 117K vertices, running at around 30 FPS, and enabling instancing allows us to get to around 46, 45 FPS. So we're probably seeing some CPU bottlenecks that's being alleviated there. Now, if we move over to using a very low poly mesh of only 1K vertices, then of course we run at 60 FPS since we have a low bandwidth. But usually we still want a mesh that has the same visuals as our high poly one. So we can use this medium one going at 30 FPS, but enabling instancing, removing that CPU bottleneck gets us all the way to 60 FPS. And here we have some examples of Qt Quick 3D specific code. On the left, we have the LOD manager for explicitly specifying our LODs. So we have 4 models for 4 LODs, and we can also choose the distances at which we change to different LODs and fade distance as well. In the middle and right, we have an example of how to do Qt Quick 3D instancing. First, we have a instance list, which is composed of instance list entries. This tells us where we want our instances to live, as well as some other properties. And we set this instance list onto our model on the instancing property.